Hello everyone, thanks for joining in. My name is Ignat, I'm from Cloudflare, and today we're going to talk about reconciling performance and security in high-load environments. A little bit about myself. I do performance and security at Cloudflare. I'm passionate about security and crypto, and I also enjoy low-level programming, so I work on Linux kernel, bootloaders, and other very scary low-level C stuff. Before we start, just for your information, this talk is pre-recorded. Unfortunately, my home broadband connection did not allow me to do live streaming of the talk, so I had to pre-record it. But I still want the talk to be interactive, so by the time you're listening to this recording, I will be online, I will be listening with you, and in the end, if you have any questions, I want you to do these steps. So first of all, go to app.sly.do and enter the event code perfsec to post your questions. Then please join my Zoom meeting. I will with this meeting code 466482145. I will be there and I will be reading out aloud the questions from Slido and answering them by voice to make it faster and make it feel more like a real life conference. And then when I go through all the questions on Slido, you can hang around in the Zoom meeting. If you have any follow-up questions, you can then ask them by voice, or you just want to have a chat in general. And yeah, basically, if you have any problems, please reach out on Twitter so you cannot join the link, you have some errors, etc. Or if you miss the questions opportunity and you want to ask the questions later, you can also send me via direct message on Twitter. All right, let's go. So performance versus security. So this is how typical companies perceive performance versus security. So usually you have some kind of security department which fights for security, tries to secure everything, and you have, well, basically the rest of the organization which fights for performance, and it's everyone pulls to their side. Some organizations are more conservative, I would say, and they're probably more security conscious, so they try to balance performance with security, because everyone perceives security as an add-on, as something which adds overhead, and if you add it too much, you lose performance. If you don't add enough, so you lose the face of your customers probably. But today we're going to talk about how you can combine performance and security, how security may help performance in the long term. And actually there are a lot of opportunities to do that. But before, I will try to explain the performance definitions I want to use in my talk. So I will use two definitions of performance. The first one is performance in the narrow sense, and it's the way how we perceive performance is. It's about speed, it's about throughput, it's about latency. But also there is a performance in the broader sense, which includes all of the above, but also it includes resource optimization, process optimization, and some other things. And I will have examples for each of those throughout my talk. Before we start talking how security may improve performance, let's discuss how security does not impact performance in a bad way. So there are still a lot of opportunities actually to implement security with a zero performance overhead. And what I mean is by that is there are several ways to do it. So sometimes the security cost or security overhead is negligible, and or it affects some kind of non-primary metric. Sometimes that the additional security cost is just hidden, or I call it amortized, by the architectural implementation itself. And sometimes the cost is not incurred for normal system behavior. I call it prohibitive security. Okay, let's discuss an example of negligible security cost. And the typical example here is secure boot chain. So what is secure boot chain? Consider a typical server boot process. So you have a system firmware, which is basically your BIOS. So when your server boots, the BIOS boots a bootloader, but with secure boot enabled, before booting and executing this bootloader, the system firmware can verify this bootloader. So if the system firmware verifies the bootloader, now you trust that bootloader, right? So then the bootloader boots the operating system, but you also trust that bootloader to verify the operating system before actually executing it. Now that you have a trustworthy operating system, you trust that operating system to verify its drivers and also the application it runs. So you build a chain of trust. So from system firmware up to your high-level application and services which run on your system. And as a result, you basically, all the software which runs on your production is signed and authorized by you. So yeah, secure boot chain ensures that all running code is authorized by the system owner. And basically, it's the most efficient protection from persistent malware, because consider if an attacker getting into your system, the first thing attacker might do is they try to persist. So even though persist in the boot chain, so even though you reboot your server, you remove the vulnerability, they still want to have the control and access they had before. So they try to inject their code into the system boot process to regain control, even when you reboot your machines. But it's not only security feature. So having implemented and enforced secure boot chain, it also enforces your operational procedures, because it not only locks out attackers from running arbitrary code on your system, it also locks out your, well, sometimes lazy operations team which tries to cut corner fixing things. So they don't have the possibility anymore to do one-off fixes. So they always, if they come up with a fix for a particular problem, the secure boot ensures that all these fixes are properly fixed in the versioning control system, because they cannot just manually compile stuff on their own laptop and push it to production. They need to go through the whole process, CI, which can properly sign the code and authorize the code to run on your production systems. And also, your system just runs only what's needed. So there is massive security and process benefit having secure boot, but it has negligible security cost, because verifying signatures at boot time just adds some milliseconds to the overall boot time, and modern servers are booting, well, like minutes, like tens of minutes. So adding a couple of milliseconds will not change anything, and it's zero cost in runtime for your services. So this is a clear example of negligible security cost, and which affects a non-primary metric. We are not that concerned with server boot time these days. The second example, let's talk about amortized security cost. And for this example, we will take data encryption at rest. So let's revise a typical storage stack. So imagine you have your applications, they read and write files from the file systems. The file systems translate these files into specific blocks and send them to the operating system block subsystem, which actually talks to real hardware. So if you need to encrypt data at rest, you can actually do it at each of those layers. At storage layer, you can just buy hardware which can encrypt the data. It's called self-encrypting disks. You can implement encryption at the block subsystem. The typical solutions on Linux is called LUKS or dmcrypt. On Windows, you may be familiar with BitLocker, and on macOS, you have the file vault. Then you can have encryption in the file system layer. On Linux, it's eCryptFS or FSCrypt. And finally, you can, of course, encrypt the data in your application. You can just add code which encrypts the data before writing it to a file, which is also easy. Like Cloudflare and many SaaS companies, they prefer block subsystem level encryption, and on Linux we use dmcrypt. And the reason for that is it's relatively easy to configure, and it's fully transparent to applications. So applications do not even know they read and write data in encrypted form, and they don't need to have any additional code to support data encryption. So the operating system transparently encrypts data for the applications. We also don't roll our own crypto. Unlike an application layer, if we try to implement encryption in the application layer, we go to each application maintainer and say, oh, you need to add code to do the encryption, and not all developers have enough training or knowledge to implement encryption properly. And the reason we don't use the hardware layer encryption, it's still the encryption implemented in your operating system, at least in Linux, is open source and auditable, so we can review the correctness and security of the implementation. So why not enable data trust encryption? Well, actually, there is almost no reason not to do it, because consider a typical service running on the internet. Usually the overhead added by latency overhead added by disk encryption is negligible compared to network latency between your server and your end user. So I'm pretty sure if a typical internet service will start encrypting data at rest, like most internet users will not notice the overhead, because the request latency to the service will be actually the same. Unfortunately, it was not the case for Cloudflare, because Cloudflare, one of the main Cloudflare products is a CDN, so we try to put content as close as possible to users, so network latency is quite low here. And as an example, here is the current Cloudflare network. We have a lot of data centers, so we aim to be in each major city and aim to be very close to the typical internet user. And in our case, when we enabled data at rest encryption, actually internet users started noticing it. So here is an example. Here we do a simple test. So the red line here is our CDN cache response tail latency from a server with encrypted disk, and in green we have the same tail latency from a server with unencrypted disk, and you can see that actually enabling encryption for us created some overhead. But we still value security very much, so we investigated the implementation of Linux disk encryption, and we were able to improve it, which is a blue line on this graph. And now we still have the full disk encryption implemented in Linux with zero encryption overhead. So why does it matter? So when we try to improve the implementation of disk encryption in Linux, we actually expected lower disk encryption overhead, but the result exceeded our expectations. So in terms of cache response latency, we got none overhead at all. So in other words, we got disk encryption for free. And actually, our improvements are not related to any crypto algorithms or formats. We use the same algorithm as the current Linux kernel does. We just redesigned the architecture a bit. And now the zero overhead data encryption is a no-brainer, so there is no excuse not to use it. But additionally, it gave us some points that we need to further research the performance of the overall system. So if we enable encryption on a system and we don't see any overhead, that means the disk encryption is not the bottleneck anymore, and that means that the bottleneck is likely elsewhere. So it creates an incentive for us to do further performance research and improve our architecture to find and eliminate that bottleneck. So in this case, security clearly drives performance research. Final example is so-called prohibitive security, and now we will talk about system calls. So what are system calls? So imagine you have your application and service running. It usually doesn't run on bare metal, so it usually runs on some kind of operating system. And the operating system provides a well-defined interface for application to do their tasks, right? Reading files or sending data over the network. So yeah, application does not read data directly to hardware. It usually goes through system calls through the operating system to write data or communicate via network. So system calls are related to a framework in Linux called seccomp. So seccomp is a security framework in Linux which allows an application to establish a so-called contract with the operating system to declare in advance which system calls it will use for its functionality and which system calls it will definitely not use. And it's a very powerful security technique. So let's check an example. So consider you are developing an application. It's a simple clock application. Of course, we're talking about seccomp, and seccomp is Linux technology. So you're developing a clock application in Linux. So if you're using seccomp, the moment your application starts, it declares to the kernel, to the operating system that, hey, I'm just a clock application. So for my functionality, I will only use get time of day system call, which basically returns the current time to the application from the kernel. And then your application just executes as normal, and in runtime at some point it needs to know the time to display it to the user, for example. So it sends a request to the operating system for the time, and because it's part of the established contract, the operating system will happily provide the time for the application. Now imagine you wrote this clock application in some kind of unsafe language, and it had a security vulnerability, and someone exploited that application and achieved remote code execution. And now your application became malicious, and it spies on you and like tracks some kind of privacy data from your system, and it needs to send this data to some kind of remote server for storage. So it will try to send the data using the send system call, but because send was not part of the contract, was not the part of what application originally intended to do, the Linux will detect it and immediately kill the application. So seccomp is a very powerful technique, and it greatly limits the potential damage of remote code execution exploits. And it's also zero cost overhead. So of course, if your application is being killed, it's being stopped, it's like 100% performance overhead because your application is not running. But that overhead is only incurred if your application starts behaving abnormally. If your application behaves normally by the contract, your application runs as usual and you will not see any performance overhead. But apart from protecting from security exploits, it also improves development velocity, because when you design the contract or the seccomp filter for your application, you as a developer, you express the intent for your application. But actual implementation may have bugs, and sometimes the application might misbehave not because it was exploited, but just because an unforeseen bug made it so. And if you see your applications getting killed for no reason, then you will have your fast feedback loop that you have a bug in your application, and it starts behaving abnormally, and you should investigate it. Okay, so let's move on to examples where security actually improves system performance in the narrow sense, and we will talk about performance in the narrow spans, which is about speed and throughput and latency. First, let's talk about HTTP 2 and 3. So what is HTTP 2? It's the new major version of the HTTP protocol, the protocol which is the most popular protocol on the internet. It's the backbone of the internet basically these days. It's a major rewrite of the HTTP.1 protocol, which is almost 30 years old by now. Unlike HTTP1 protocol, it's a binary protocol. It has some other features like connection multiplexing. So with HTTP1 protocol, you could only have one HTTP connection in one TLS connection. With HTTP2, you can have multiple HTTP connections in a single TLS or a TCP connection. And also HTTP2 has a server push functionality where servers can proactively push resources to clients, not waiting them for explicitly to request them. There is also HTTP3, which is still not standardized, and the major difference of HTTP3, it doesn't run on the TCP protocol anymore. It runs over the new QUIC protocol, which is a small implementation over the well-known UDP protocol. So what about HTTP2 performance? So back in 2015, when the protocol was just standardized, we implemented it and for our corporate website. So we tried to serve our homepage over HTTP2, and we immediately saw a 100% performance improvement. So via HTTP2, our homepage loaded like twice as fast. Here is also an interesting demo which visualizes the speed difference between HTTP1 and HTTP2. So you can see on the right side the same image loaded by HTTP2 is loaded much faster. So HTTP2 is a no-brainer. We all want to have it, and if you have a service owner, most likely you wanna support HTTP2. But there is one thing, that HTTP2 is only supported via TLS, and only via TLS. So although the standard itself does not mandate implementing HTTP2 over TLS only, there are no de facto mature implementations of HTTP2 protocol via plain text TCP. So then basically, of course, you can implement it yourself, but then you can balance the resources. You can either just spend a little bit of resource configuring and enabling TLS for your web service, or you can just rewrite the whole HTTP2, which is very error prone and hard to make it right for the first time. So yeah, if you want the performance of HTTP2, you need to have TLS, where security improves performance. Speaking about TLS, so in this picture we see the typical TLS handshakes, TCP and TLS handshake. So in blue you see the three-way TCP handshake, and in yellow you see the TLS handshake. The important bits here is these two steps of the TLS handshake, where the client and the server, they agree which crypto algorithms they will use for the current session. And for the asymmetric crypto, there are two major choices these days. You can either have an RSA signatures, or you can have ECC signatures, which stand for Elliptical of Cryptography. So what is an RSA? It's an older crypto system. It was proposed in 1977. It's based on a hard problem of factoring large numbers. It has a sub-exponential complexity cracking algorithms. So in simple words, what this means, sub-exponential means semi-efficient. So the cracking algorithms for RSA, modern cracking algorithms, are not efficient yet, but they are not very inefficient as they used to be. That's why, so that's like kind of semi-efficient. So that's why to make RSA secure these days, you need to use very large key sizes, more than 2048-bit is standard today. To compare with RSA, ECC or Elliptical cryptography is the newer crypto system. People call it newer, but it's actually quite old as well. It was first proposed in 1985. Its security of ECC is based on another hard problem, which is called discrete logarithm problem over elliptic curves. And unlike RSA, this problem does not have even semi-efficient cracking algorithms yet. It's only very inefficient cracking algorithms. That's why ECC is considered more secure and also requires smaller key sizes. Currently, most people use 256-bit keys. Okay, let's compare the speed of RSA and ECC signatures. So if you run this, I run this on one of our servers, and we can see immediately that ECC signing is around 15 times faster than RSA, which means you get 15 times faster TLS handshake if you configure your web service to use ECC instead of RSA. But you have other benefits as well. You get less CPU utilization. I will come back to this just in a second. You also have less key storage because ECC requires smaller keys than RSA. And of course, you get better security because ECC is considered more secure. Coming back to CPU utilization, back in 2017, we did a measurement in one of our data centers. So we actually measured the efficiency of different crypto algorithms and how much of CPU we spend doing these. So take a look at the middle graph. Here you can see that during the measurement we were able to establish 75% of TLS handshakes using the new elliptic curve signatures, and 25% of the handshakes were established using RSA signatures. But if you look at the right graph shows of how much percent for each crypto algorithm we spend from the overall percentage we spend on crypto on the server. So like if we take all the CPU cycles we spend on crypto during this particular measurements as 100%, 50% of these CPU cycles were spent doing RSA. So just to reiterate, 50% of the time us doing only crypto were spent serving only 25% of TLS connections, and only 12% of all the crypto time we spend on the server allowed us to serve 75% of TLS connections. ECC definitely faster, better, and more secure with RSA. Many service owners do not enable ECC because they fear of compatibility, so they fear they will lock out potential users with old clients which do not support HTTP, like especially like small IoT devices. But actually, most modern web servers, they have like a fallback implementation, so you can configure both RSA and ECC TLS certificates for your service. So your web server will serve ECC certificates to the clients which declare support for ECC, and they will serve RSA certificates to clients which do not declare support for ECC. So ECC enabling is a no-brainer, and you immediately get many performance benefits here. All right, let's zoom out from the single server and let's talk about internet. So internet is a very huge decentralized network, so it doesn't have any central point of coordination. So it's basically a network of networks, many small networks interconnected with each other. These small networks, in internet terminology, they're called autonomous systems. And the way how these networks communicate, the way how your network knows how to send data from your computer to the remote service on the other side of the world, is established via BGP or Border Gateway Protocol. So each autonomous system or network, they announce via BGP the resources they own. So for example, this network here announces that they own and serve 1.1.1.1 IP address, which is basically a Cloudflare address. Another network announces support for 8.8.8.8, which is a Google IP address. And networks do not only announce their resources, they announce their neighbor resources and neighbor resources. So the whole IP information is propagated throughout the internet, and each network knows how to send packets from one network to another. But these announcements determine the state of the internet, but the state of the internet is not constant. Links come up and go. Some networks have performance problems, so the state of the internet is continuously reconfigured. So are these announcements. And sometimes, because of this misconfiguration, the data from point A to point B may not travel in the same path. So that's why you have so-called packet switching networks. So chunks of data may traverse different paths of the internet, and they're basically reassembled when they receive the final point. One problem with internet and BGP in particular is security. And because BGP is a quite old protocol, it originally didn't have any security considerations, and the whole security was based on a simple gentleman's agreement model. So each network will announce resources they own, the resources or IP addresses they own, and they don't announce the IP addresses they don't own. Of course, in such a system, there is always a possibility for a malicious entity to appear and start announcing resources they don't own and basically impacting the state of the internet. So in this particular scenario, if you have two networks announcing the same IP address, traffic may travel to one network or the other network, and with regards to a specific network, the actual owner of the IP address, some traffic to their IP address may be lost because they went to the attacker. To combat these problems on the internet, BGP was upgraded with a extension called RPKI, which is basically stands for Resource Public Key Infrastructure. In a nutshell, it means that the owners of the resources are now signing their announcements, and the other networks are the legitimate good networks are expected to verify signatures of those announcements before propagating these announcements further down the internet. So implementing the security helps to lock out these malicious actors from the internet. However, RPKI prevents bad actors from claiming resources they don't own, but these false announcements or these false claimers are not always bad actors. So sometimes a network may announce invalid IPs because of some kind of misconfiguration. Imagine an operator configuring a network equipment and just fat fingering a number, and like the network immediately starts announcing the IP address they don't own. Or there may be also bugs in network equipment software which may corrupt the announcement in some way that it will start announcing invalid resources. So in this case, RPKI also helps because such misconfigurations are not accepted by the rest of the internet. Therefore, traffic is not lost. And just to clarify, these bad announcements may not cause like strictly denial of service. So from the viewpoint of a typical internet user, it's just some traffic is being lost. So internet protocols were designed around reliability. So even though like some packets may not travel to the intended end destination, your operating system will likely retry and resend them. So you will get your connectivity up, but from the viewpoint of an end user, that connectivity may not be just fast enough. You just get a bad connection with packet loss. So so these are like so some minor misconfiguration just create packet loss, and some misconfiguration depending on where they happen on the internet may cause severe outages. And one of the outages is outlined in our blog post, which is at the bottom of the slide, which is a very fascinating read, by the way. But here we have the example of security improving performance. If we implement RPKI, we're more reliable and less reliant on these false announcements. So we will just not accept the invalid announcement from the other networks. Therefore, the throughput of the internet is actually improves and doesn't suffer due to these misconfigurations. Okay, so let's talk about security and process performance. So sometimes you just can't improve, your security does not improve performance in the narrow sense, but it may improve performance in the broader sense, or in the longer term. Let's consider a Cloudflare example. Again, if you remember, this is the Cloudflare network. We have a lot of data centers and we're continuously expanding this network. So we bring up new data centers quite often. And consider the process of bringing up a new data center. It's actually quite complex. So we have to connect the hardware. It's actually done for us by the staff in the data center itself, but then our operations team has to verify that hardware, and there are multiple steps involved. So we need to set up initial network because this is a new data center, it doesn't have anything. Then once we have the network, we need to configure the out-of-band access to our servers. Then we need to secure that out-of-band access, because usually on new hardware the out-of-band consoles come with default insecure configuration. Once we've done that, we need to dump all serial numbers from all the components on the server and cross-check them with our inventory system to ensure we actually received the hardware we ordered and no components were tampered with in transit. After we are done verifying the server, we do initial key provisioning. So we need to set up some kind of initial key management. It's usually either SSH or configuration management keys. So we need to push those keys to the server. And then we need to verify and authorize key fingerprints. You know, when you SSH to a server for the first time, it usually says, hey, here is a fingerprint for the server, and ensure you're talking to the correct host. And we need to do it, repeat this procedure for each new server, which is basically a very repetitive, boring, error-prone process. So how can we improve it? We can try to do it with a TPM. So what is TPM? TPM stands for Trusted Platform Module. It's a tamper-resistant crypto chip in modern laptops and servers. So most likely even your laptop has a TPM. You haven't used it yet. Like any crypto chip, it can provide secure key storage and hardware random number generator. But for the purposes of this example, what's important from the TPM, it's a fundamental building block for remote attestation. So remote attestation is a communication process which can provide you with two things. It can provide authenticated identity for remote systems, and it also can provide you with trustworthy assertions about the state of the remote system. The state basically means which software the remote system runs. So what can we do with the TPM? Let's go through the remote attestation in detail. So let's imagine you have a verifier. In our case, it's the Cloudflare network, and you have your new hardware like this remote server, and it has a TPM. So the verifier can send a request to the TPM, which is called a quote, and in response, the TPM will provide its identity, and it also will provide the state of the remote host. Basically, it will state all the software which runs on the remote host, and it will sign that response, so the response cannot be tampered with in transit. So by the time we executed this procedure called remote attestation, we know that we're communicating with the right host. We know we're communicating with the right host securely because the response was not tampered with, and we also know that the remote host runs only authorized software. It runs the firmware we expect, it runs the operating system we expect, it runs our operating system, and all the other services and a user space application is what we expect. So we can basically trust that remote host now. So because you can trust that remote host, you can enable automation to do most of the procedure. So now with the TPM, you can have a service which can verify the new hardware identity. It can verify the running operating system. It can then cross-check the serial number, so you can actually trust the remote server to cross-check its own serial numbers by itself. And then because you have a secure channel through the TPM to the remote host, you can provision configuration management keys. And once you have the keys, your configuration management can configure the server properly and start serving production traffic. In the meantime, what your real people, your real operations team do, well, they basically can have tea or work on interesting things or just have a great work and life balance. So TPM also provides you a way to build better automation, which creates less room for human errors and misconfiguration, which in turn makes data provisioning faster, so it improves the speed of the overall process. And also it gives you back efficient engineering time, so engineers can develop and improve systems rather than just doing some repetitive, boring tasks. And because it's a security feature, you just get better security, which is a nice add-on here. That's basically it for today. So let's review what we learned. So we learned that security does not always have to impact performance. Remember the zero cost security. There are a lot of opportunities out there to add security without incurring performance overhead and still be in a better place than in having just an insecure system. Sometimes actually security improves performance in the narrow sense. Remember HTTP2, remember the BGP, and remember the TLS ECC versus RSA discussion. If a certain security feature cannot improve performance in the narrow sense, maybe it can improve performance in the broader sense and in the longer term. Remember the performance improvement the process performance improvement brought to you by starting to using TPMs for data center provisioning. And basically, if you're on a security team and you want to prioritize security work within your company, thinking about how the security can improve performance is a nice approach to communicate your goals to the rest of the company, because performance is what the rest of the company understands. And if you start speaking their language, basically you have a better chance to get your project on board and get it done faster. Yeah, that's basically it, what I wanted to say for today. Thanks again for listening. Now we're ready for questions. Go to app.slide.do, enter the event code perfsec and post your questions, please. Then join my Zoom meeting with the meeting code 466482145 to hear me answer these questions. And if you want to chat, just stay around in the Zoom meeting, and once I go through all the questions from the Slido, we can have some follow-ups and just chat. Thanks. Hope it was useful. Hope it was as interacting as live, and stay safe and be well. Bye.